So today we will start about the quotient groups. So what are quotient group? Quotient group are group made by the cosets bound by a normal circle. So it is denoted by quotient group is denoted by G. G is the group. H is a normal subgroup of G. That is H is a normal subgroup of G. And by G by H, we means all the set of all the cosets, and this set of cosets will form a group. Will form a group. That is, it will satisfy the closure property. It will satisfy the associative property. It will satisfy the your identity, which will be your H itself, and it will also have your inverse. Also have your inverse. It can be commutative, can be non-commutative. The group can be abelian, group can not be abelian. Okay. So I'm saying that G by H equal to HA. Okay. HA where A belongs to G. It can also be denoted by AH where A belongs to G. Both are fine. The reason being, for a normal subgroup, H, AH is equal to H. This is true. This holds. Not always, but for a normal subgroup, this is always true. AH equal to HA. So you can denote it either way. G by H equal to HA or G by H equal to A. Both notations are fine. Okay. So let's see what is the structure of the group. Let's take a group. This is a group G. This is a cyclic group. 1 minus 1 iota minus iota. Right. This is a normal subgroup. This is a group. Okay. This is a cyclic subgroup. Cyclic subgroup. Every cyclic group is abelian, so this is also abelian. Okay. And in an abelian group, every subgroup is normal. In an abelian group, you can prove that also. Okay, because if a group is abelian, let's say G is abelian. If I take any A belonging to some subgroup H, okay, and I take X belonging to the abelian group G, then X inverse will be equal to X inverse. Because the group is abelian, this will commute, right? This will commute. So I can write it as X inverse A is equals to X inverse A is equals to EA equals to A, which will always belong to H. So XA X inverse will always belong to H for a abelian group. Therefore, every subgroup of an abelian group is normal. Okay. So in this group, I can take the subgroup 1 minus 1. The group is 1 minus 1 iota minus iota, and subgroup H is your 1 and minus 1. What will be the cosets? Here the okay, in cosets also now you can denote it in two ways. You can denote it as HA AH, or you can denote it as H plus A plus H, depending on the operation. If the operation is multiplication, you denote it as HA AH. You can denote it H plus A plus H if it is addition. Okay. Here the operation is multiplication, so we will denote it as HA. So what can be the possible cosets? So first, let's say if I do 1H, it means that I am multiplying 1 by the complete subgroup. So if I multiply 1, it will be 1 into 1 and minus 1 into 1. It will be again 1 minus 1 itself, which is equal to H. So 1H equal to H minus 1H. Okay, so minus 1 into this 1 minus 1, it will be your minus 1 and 1. This is again H, only the order has changed. In a set, order doesn't matter, right? So This is also equal to h. So 1h minus 1h equal to h, and I will tell you why this happens. Okay, but let's say iota h. Now it will be your iota, and then this will be your minus iota. Okay, this is unique. This is different from the first h. Minus iota, then this will be your minus iota, and minus minus plus, this will be your iota. This will be your iota. So these are again same. These are again same. So what are the cosets of that you have got for g equal to 1 minus 1 iota minus iota, h is equals to 1 minus 1. The cosets, there are only two cosets. Okay, only two cosets are there. So 1 minus 1. Okay, two cosets are there. One is h itself, and the other is iota h, or you can say minus iota h. Both are equal here. Iota h equal to minus iota h. Okay. So only two cosets are there. The first thing you should know is ah equal to h. This happens when a belongs to h. Why this happens? Because of the closure property. Closure property. HA equal to H happens when there is a, because of the closure property. Because if H is a subgroup, that it has all the properties of a group, that is, it will follow the closure property obviously. Now, if I take any element belonging to H, so and if I take any element X belonging to H, then AX will always belong to H, right? So that is why when you multiply, okay, B1, B2, let's say all okay, Bn, then ABn, AB2, all ABn. Now all of these will belong to H. So what actually happens is element doesn't change, the set does not change, only the order of the set changes. Like this, what happened in your minus 1H? What happened in minus 1H? Because minus 1 belong to H, so it will also give you H only, but only the order change. 1 became minus 1 and minus 1 became 1. So if any element belongs to the subgroup, then AH equal to H, you will always get the same subgroup. Okay. You will always get the same subgroup. And if it does not belong to that group, then you will get some new subgroup. Okay. Here iota H and minus iota H are equal. Okay, that can be checked also, because there is a property which says if AH equal to BH, this implies that AB inverse belongs to H, and this is a both. This is true for both ways. AB inverse belongs to H. So if you see what is AB inverse, A is iota, B is minus iota. Okay, minus iota. And what is the inverse of minus iota? Okay, 1 by minus iota is iota. So AB inverse will be iota into minus iota is equals to iota into iota, which is equal to minus 1, and minus 1 belong to H. So therefore AB inverse H, AB inverse H will be equal to H. Okay, it means that AH equal to BH. These kind of things happen. You will eventually get very comfortable in this, but it initially will face some resistance to register this. Okay. Let's see how we write a quotient group, or G by H, I said, is a subset of all the cosets, right? So for let's say G, again we take the same group minus iota, right? H is your 1 minus 1. Then you, and I know G, this is a normal subgroup. This is a normal subgroup. Why it is a normal subgroup? Because G is abelian. G is abelian. And in an abelian, every subgroup is normal subgroup. We just proved that. So G by H is only possible that this notation is only happens when H is a normal subgroup. H has to be normal for the quotient group to exist. Okay. Then G by H is equals to your first is H itself, that is 1 minus 1, and the second will be your iota H. Iota H. Because only two are there. Even if you write minus iota H, it is same as iota H, so it doesn't matter. And in a set, you don't write repeated items, right? This is a property of set. You don't write AAB. This you only write it AB. You don't write repeated elements in a set. This is wrong, right? So H iota H. This is a quotient group. This is a quotient group. It is a group of subgroups. If you want to expand it and write, so it will look something like this. G by H is equals to, okay, G by H is equals to 1 minus 1, comma, okay, iota minus iota. This is the, okay, G by H for the given group. Any doubt till now?
No, sir.
No, sir. Continue it. Fine.
So the way actually why it is called a quotient group is, if you take a group G, okay, if you take a group G and then you take your normal subgroups, let's say H here, okay, then you can partition it as AH, BH, okay, CH, DH. You can partition it like this. You will get, why partition it? Because if you see, all the elements have same number of all the members have same number of elements. This will have 2 elements. This will also have 2 elements. If there were more cosets, they will also have 2 elements. So you can partition it in equal parts, right? All these rectangles will have equal area. That is, you can partition it equally, and that's how the name came. Okay, that is when you divide something, you get a quotient. That is the way. Because this number will be, if you the number of elements will always be equal to index of H. Index of H in G. Okay, G in H. That is number of elements in G by H. Mod is equals to order of G upon order of H. That is mod G by mod H. Okay, let's check. So G has 4 elements. H had 2 elements. So G by H has 4 by 2 equal to 2 elements. Yes, it had, in our case, yes, G by H has 2 elements. What are the 2 elements? One element was H itself, other element was iota H, right? So this is the case. This is also always equal to the index. Number of elements is equal to index. Okay, what is index? Order of G upon order of H. This is the basic idea of what is a quotient group. What is a quotient group? Okay, what is a quotient group? What is the identity in a quotient group? Identity in a quotient group. What is an identity? So in G by H, we have elements of the form HA for A belonging to G, and we have already discussed, we can also write it as AH. Both are, because both are equal for a normal subgroup. Okay. Now, what is the identity? H is the identity. Always H is the identity, because H itself is always part of the group. Because their E belongs to G. For E belongs to G, HA will be equal to H. Not E, any A belonging to H also belongs to G. And we know that HA will be equal to H for all A belonging to H. So you will always get H as a member of the quotient. Therefore, H is the identity. Okay, H always exists, and it is always the identity of the G by H group. Okay, you should remember this. Why it happens? Because what is an identity? If I say HA into HB equal to HA equal to HB into HA, then I can say that HB equal to identity, right? Because elements are of this form, right? This is the definition of identity. Does H satisfy it? Yes, H satisfies it. So HA into H is equals to HA, right? Because this is the property of cosets. HA into H is equals to HA. Similarly, H into HA also is equals to HA, because HH equal to H for any subgroup, not just normal subgroup, for any subgroup. And the basic, you should know the basic operations in a coset. HA into HB is equals to H of AB. From HA into H, it is in HE. You can see H can be written as HE also. Okay, HA into HE, it will be HA, it will be HA. So you will so it satisfies the property of the identity. It is the identity of the quotient group. H is the identity of the quotient group. Any doubt in this? What else do you want to know? This is the basics, okay, of the quotient group.
No doubt, sir.
Now you can write different. Uh,
Sir, in this,
yes. What are you saying?
Sir, in this part, if you can explain some theorems you can take on quotient group, it will be very beneficial for us.
The first theorem given in the book is if G is abelian, G by H is abelian. Okay. That is G is abelian. G is abelian implies G by H is abelian. Okay. So you should put a note that converse is not true. Converse is not true. You can have a quotient group such that the cosets commute with each other, but the element might not commute with each other. That is the example being the second question of the 2.3 exercise. 2.2 exercise. Okay, so let's see. Now we know that for any AB belonging to G, A belonging to G, we have AB equal to BA, right? Because G is a BA. Now G by H Okay, we'll have elements of the form H, that is cosets, where A belonging to G. So we can have, let's say, HA and HB belonging to G by H, right? Let's say then HA into HB is equals to HAB. This is a simple property of cosets, right? Now we know that AB equal to BA. AB equal to BA. Okay, from because G is abelian and AB. So this can be now written as HB into HA. Into HA. Hence, therefore, HA commute with HB. This implies G by H is abelian. G by H is abelian. This is a very easy. This was a very easy. Oh, very,
एक्सक्यूज मी सर
yes.
सर यहाँ पे जब भी हम लोग को प्रूव करने बोलता है अबिलियन, तो क्या मतलब पहले से ग्रुप हम लोग मान करके चलेंगे या फिर मतलब बस ये कम्यूटेटिव प्रॉपर्टी दिखाने से हम लोग कह देंगे कि अबिलियन है?
हाँ, मतलब this is a given fact that G by H is a group. So the only thing that you need to show is that it is commutative. You don't have to.
मतलब कितने सर 15 मार्क्स का भी क्वेश्चन आएगा तो भी हम लोग इतना करके छोड़ सकते हैं ना?
हाँ, अगर 15 मार्क्स का भी आएगा तो हम यही इतना ही करके छोड़ेंगे, ठीक है?
ओके,
Otherwise वो आपको ऐसा बोले prove that it is a like group and it is also abelian. तो दो अलग-अलग स्टेटमेंट देगा आपको.
सर जब 10 मार्कर्स क्वेश्चन होते हैं या 12 मार्कर्स, तो उसमें हम जैसे साइक्लिक ग्रुप के बारे में हमें अबेलियन प्रूफ करना हुआ या फिर कुछ ऐसे जो क्रॉस के होते हैं, तो हम यहाँ डायरेक्ट वैलिड रीजन देख के दिस इज साइक्लिक ग्रुप, दिस इम्प्लाइज दैट इट्स अबेलियन और इसके सब ग्रुप सारे अबेलियन होते हैं, तो ऐसे करके हम छोड़ सकते हैं। या फिर मतलब 15 मार्कर्स में तो हम प्रूफ करेंगे सारा अच्छे से, बट ऐसे में हम बस रीजन दे के उसको सेलेक्ट कर दें।
समझा नहीं आपकी बात?
सर मैं ये कह रही थी कि जैसे कोई साइक्लिक ग्रुप दिया है, तो साइक्लिक ग्रुप से रिलेटेड अगर कोई सब ग्रुप है और हमें पता है पहले से कि हाँ इसका ये सब ग्रुप होता है और वो अबेलियन होगा, अगर उसे अबेलियन प्रूफ करने के लिए कहे जैसे ये पूछ रहे हैं, तो 10 या 12 मार्कर्स क्वेश्चन होते हैं जो मतलब 15 मार्कर्स नहीं है, तो उसमें हम बस रीजन देके कि मतलब ये इसका सब ग्रुप है और इसका ग्रुप जो है साइक्लिक है और हर साइक्लिक ग्रुप अबेलियन ग्रुप होता है और अब सारे मतलब साइक्लिक ग्रुप का जितना भी सब ग्रुप होता है वो अबेलियन होता है। मतलब ऐसे वैलिड रीजन के साथ फिनिश कर सकते हैं जैसे हम लोग कॉम्पिटिटिव एग्जाम में अक्सर करते आए हैं।
नॉर्मली तो आपको प्रूव करने को बोलेगा, अगर कोई भी इजी थ्योरम होगी तो यू शुड गिव द प्रूफ बिकॉज़ इट विल बी ऑलवेज बी आस्किंग फॉर अ प्रूफ टू प्रूव दैट this subgroup will be every sub group, every cyclic group is abelian, that kind of thing. Then you will be giving proof. You will not be writing statement only. But अगर उस चीज का यूज करके कुछ हमें अलग चीज प्रूव करनी है तो डायरेक्ट स्टेटमेंट लिखो और उस चीज को प्रूव करो।
ओके सर वन डे ऐसे एक मैट्रिक्स का क्वेश्चन था जो क्लेन 4 का था, मतलब वो हमें मतलब डायरेक्ट में अगर देखें तो प्रॉपर्टी उसकी क्लेन 4 से मैच कर रही थी, तो उसका जब हम टेबल हमें मतलब जो उसका कंपोजिशन टेबल बनाना था तो वो तो हमें क्लेन 4 का पता होता है कैसे होता है, तो डायरेक्ट अगर हम उसे रिकॉग्नाइज कर लेते हैं एट दैट टाइम कि हाँ ये उसी का है, तो डायरेक्ट हम उसकी हेल्प से कर सकते हैं। या एक एक मैट्रिक्स जैसे 8 मैट्रिक्स से हमें मल्टीप्लाई करनी पड़ी थी, तो इतना सारा मल्टीप्लिकेशन करने से बेटर होगा।
आप मल्टीप्लिकेशन मत करो, मतलब आप शो कर दो मल्टीप्लिकेशन। अगर आपको पता है कि वो क्लाइन फॉर ग्रुप है तो आपको पता है कि भाई a स्क्वायर इक्वल टू b होगा, तो आप मैट्रिक्स को मल्टीप्लाई क्यों कर रहे हो? आप वहां पे सीधा लिख दो।
यस सर, डायरेक्ट कंपोजिशन टेबल
मतलब आप ऐसे ले लो
तो
a is equal to some matrix, b is equals to some matrix and c is
हाँ ऐसे ही लिया
देन
था
आप
सर।
बोल दो ए स्क्वायर इक्वल टू ए स्क्वायर इक्वल
हाँ ये क्लेन 4 की प्रॉपर्टी
ओके
यहाँ पे यूज
सॉरी
कर सकते हैं।
1001 इक्वल टू बी स्क्वायर इक्वल टू सी स्क्वायर, उसका कॉम्पिटिशन टेबल आप ऐसे ही बना दो अपना
यस सर।
ई ए बी सी, ई ए बी सी, बात आप उसको ऐसे लिख दो। So second theorem is G by H is cyclic if H is cyclic. So again same वही करना है. Okay कि G is cyclic. So the let's say इसका order n है. Okay, let's order of G a to the power n equal to ये चीज है. So if I take HA belonging to G by H, then h of a to the power n is equals to h होगा, तो because ये e हो जाएगा. अब now h a to the power can be written as ha into ha into ha n times, ये equal to h हो जाएगा, यानी कि h a to the power equal to ha. Okay, so okay. Order of ha divides n, ये आपका सेकंड क्वेश्चन है ग्रुप का, सेकंड एग्जांपल है शायद, ठीक है. तो ये था सेकंड कि अगर yes, if H is a normal subgroup of G and G is of order n, then prove that order of HA divides n. तो ये आपका सेकंड पार्ट था. ओके, ये आपका सेकंड पार्ट था. ओके, नाउ अभी हमको प्रूव करना था कि H एन बी साइक्लिक होगा. सो हमें पता है कि अगर G साइक्लिक तो फॉर तो all elements will be generated by some element. Let the generator be A. So G can be written as like this, where A is the generator. ठीक है. तो G by H will have the elements like H of A to the power some X, where A to the power X belong to G. Right. Now we can say that H A to the power X equals to HA to the power X. Okay, so you can say this is the generator. It is HA will become the generator of the G by H group. ये आप शो कर सकते हो. ठीक है. I think meeting almost over हो गई है. I am left with 2-3 minutes. Okay, 2-3 minutes. So आप try the theorems yourself. Okay, try the theorems yourself. कोई भी इशू आएगा तो you can always ask me in the group. मैं एक क्वेश्चन ले लेता हूँ जो कि बहुत अच्छा क्वेश्चन है, किसी ने ग्रुप में पूछा भी था, आदित्य से शायद पूछा था. ये है एक्सरसाइज का क्वेश्चन नंबर 2.3 का क्वेश्चन नंबर 2. ओके, एक्सरसाइज का क्वेश्चन नंबर 2 मैं वो ले लेता हूँ क्योंकि वो बहुत अच्छा है. तो क्वेश्चन में एक्चुअली क्या है, आपको एक ग्रुप दे रखा है मैट्रिसेस का, और आपको सब ग्रुप दे रखा है मैट्रिसेस ऑफ द टाइप 1 0 1 1 b where b is a real number. ओके, तो पहले तो आपको प्रूव करना है कि दिस इज नॉर्मल, और ये आप इजीली प्रूव कर लोगे. दिस इज अ नॉर्मल सब ग्रुप ऑफ मैट्रिसेस. ओके, ये आपका, तो ये आपका इस टाइप का मैट्रिक्स दे रखा है, ए 0 सी डी टाइप का ग्रुप दे रखा है. तो ये आप प्रूव कर दोगे. उसके बाद आपको प्रूव करना है कि अब आप G by H इज अबिलियन. जो हमने पढ़ा था ना, मैंने बोला था कि अगर G अबिलियन है, G अबिलियन दिस इंप्लाइज G by H इज अबिलियन. लेकिन मैंने बोला था कि नोट कर लो कि कन्वर्स इसका ट्रू नहीं है, क्योंकि ये बहुत अच्छा केस है. So you can see that G by H is abelian in this case. If you will find the cosets, G by H will come out to be abelian. but G is not abelian. G is a set of matrices which is non-abelian. So even a non-abelian group can have a quotient group which is abelian. This should be kept in mind. तो यहाँ पे prove करना है. Okay, the last part to prove. Okay, that G by H is abelian. G by H is abelian. ये थोड़ा tricky task. It becomes a little tricky task because normally हम कैसे abelian prove करते हैं that AB equal to BA. पर यहाँ पे we don't need to prove. If you show AB equal to BA, it is not true because the group is non-abelian. Here you have to show that HA HB is equals to HB HA. You have to show this. But the problem is H is a infinite set. How can you show that each and every set is equality itself? That cannot be shown easily. So इसका we use the properties of cosets. How do we show? अगर मैं बोल रहा हूँ HA equal to this है, okay. So all I'm saying is HAB equal to HBA है, okay. And we know that if HA equal to HB होता है, then it implies that AB inverse should belong to H. AB inverse should belong to H. तो इसको property को using this property यहाँ पे what I can show is that AB into BA inverse should be a member of H. So when you in this question, this is to be shown. You have to show that AB into BA inverse is a member of H. That is, it will have the form of 1, 0, 1, B. So AB into BA inverse for any elements of the matrix G. Okay. Finally, it will reduce to this kind of form: 1, 0, 1, B. Okay. Okay. 1 B 0 1. So you have to show this. If you show this, then you can say that the G by H is abelian. So normal जो हमारा method होता है, you cannot show that it is commutative that easily, but you can, if you can prove this, then you can imply that it is commutative using the property that if AB inverse belongs to H, then HA equal to HB. So what I am showing that AB into BA inverse belong to H, so it will imply that HAB equal to HBA, which will imply that HB is equals to HB HA. This implies that G by H is abelian. So this is a very good question. A little unique in this sense. Okay. So ये question, keep this question in mind because this is important for two reasons. The first reason being that how to show that cosets are abelian, our cosets are commutative with each other. And the second thing is this is a counterexample of that. If G by H is abelian, then G need not be abelian. Okay. So like many, you can see its application in many questions. Okay. Like in case of permutation groups. Okay. In case of permutation groups also. Permutation group in general are non-commutative. They are not. They can never be like. Then they can never be abelian. Right, computation groups, but they're non-commutative. But you can find their quotient groups which are abelian. That kind of things will be there. Okay. Any doubt? Anything? Okay. So Anmol has asked me how HH equal to H for a subgroup, right? This also happens because of the same reason, that is closure property. Okay. Like we took the 1 minus 1 and then you take 1 minus 1. Now multiply. Okay, what are the possible things? You will get 1 into 1, 1 into minus 1. You will get minus 1 into 1. You will get minus 1 into minus 1. Okay, you get 1, minus 1, minus 1, and 1. In inside we don't read, we don't write repeated items. So this will be 1 minus 1, which is equal to h itself, right? From this you can say that h equal to h equal to h. This all happens because of this is the different way of like showing the closure property. Okay, so this is the illustration of h equal to h. Similarly, you can show that h equal to h if